All right, today's lecture we're going to be discussing thermochemistry. It's our introductory lecture to thermochemistry, so we talk a little bit of background information, kind of give you a general introduction to talking about heat. Now, we've discussed heat and energy in chemical reactions a couple times beforehand. Energy in chemical reactions. We define energy as the capacity to do work. That's our physics definition. Okay? We get a little bit closer to physics in here today than we normally like to do. Or, more focused on chemistry, producing heat. Producing heat or absorbing heat is really what we're going to focus on with today's lecture. Now, energy is broken up into two categories. We have potential energy and kinetic energy. I want to quickly define those two without getting a physics teacher in here to give us a 15-minute lecture on it. So, potential energy, what do we have? Stored energy. Yeah? Is that a good definition? We like it? Okay. So, potential energy is just stored energy. Kinetic energy. How do we describe kinetic energy simply? Yeah, energy in motion or energy of motion, I think, is probably the simplest definition that we can have. So we all remember from physics land last year or this year, we have the pen. The pen is in my hand. It's in the air right now. It's not moving, so therefore the pen has what type of energy? Potential energy, exactly. I drop the pen, okay? The pen starts to fall through the air. The pen is taking its potential energy and converting it into kinetic energy, yes? All right. What unit of energy have we discussed in this class already? Joules, yes. So we have the definition of what a joule is here. Okay. Joules we represent with a capital letter J, and joules is defined unit-wise as a kilogram times meters squared divided by seconds squared. Calories, another unit that we use to measure energy, is the energy required to raise 1 gram of water 1 degree Celsius. And then down below here, I gave you the conversion factor between the two. Give you a couple moments to copy that down, and then we'll move on. All right, so those are our two units that we have, conversion factor between the two. Everybody realizes that these calories are not the calories that you see on a package of food when you eat it, correct? Okay. The FDA forces everybody to put these nutrition labels on there. When you read a donut has 350 calories, those are actually kilocalories. Okay? So 350 calories in a food item actually means you've got 350,000 of these type of calories. Does that make sense to everybody? Okay, everybody see how those conversions work? All right, yeah, it is a lot of energy from a donut. Good. Moving on. Now, all thermochemistry has two basic parts to it. Okay? We have the system, which we define as our chemical reaction. We also have the surroundings, which is the rest of the universe, everything around it. Now, I want you to think for 30 seconds what the answer to this next question is. When we have energy transferred from the system to the surroundings, what type of reaction do we have? Now, this is going to require you to kind of backtrack a little bit. Remember when we were talking about Le Chatelier's principle about 2-3 units ago? We talked about temperature. What were the two terms we used to describe chemical reactions? Exothermic and endothermic. So when we have an energy transfer from our system to our surroundings, which one of those do we have? Everybody come up with an answer in your head. What is it? Which one? Exothermic, exactly. Which means then when we have energy going from the surroundings to the system, we have an endothermic reaction. And those two statements are kind of summarized down here at the bottom of these notes. I'll give you a moment to write those down. All right, so a quick summary list of these two terms here. Exo and endothermic reactions. First of all, exothermic reaction feels what to us? Hot, warm. Okay, when you touch a container that has an exothermic reaction occurring in it, you're going to feel that heat that's being generated. Okay, that makes sense to us. It's going from the chemical system to its surroundings, the beaker, your hands, so on and so forth. Yes? All right, endothermic is going to feel what? Yeah, it's going to feel cold to us. That's because as you touch it, that reaction is taking heat from its surroundings. So your hand is warm, it's removing that heat from your hand to continue to have that reaction process and finish. Now, what do the reactions look like? If we use the term R and P to represent our reactants and our products, where is energy going to be for an exothermic reaction? The product side, yeah. We're going to have energy on this side. Where is it going to be on the endothermic reaction? Obviously, yeah, the reactant side. So we're going to have energy on this side of the equation. Questions about that? All right, the next screen has 2 graphs that are rather involved and 5 terms that are defined below. So I'll move to that and give you a couple minutes to copy those down, and then we'll discuss what we have on those graphs. So a couple of things we want to point out on these graphs before we start to dissect them. First thing, the x-axis. We have time where time is 0 on the left and time is a certain amount of time has passed on the right-hand side. Number-wise, it's kind of irrelevant. Okay? On the y-axis, again, we have energy increases from top to bottom. I'm going to throw out some random numbers, and they are just numbers for demonstration purposes. I'm making up these numbers. Really, in terms of the actual values, it's irrelevant. Okay? So, the next thing I want to point out is R and P. You saw me use that on the previous page. R stands for reactants, and P stands for products. When we look at the first graph, the exothermic graph, we have our reactants that have a certain amount of energy. Let's say it's 10 kilojoules there, okay? And our products have 2 kilojoules. What I want you to do when we think about this delta H, the difference between reactants here and products here, delta H we define as enthalpy, the heat of the reaction. When delta H is negative, you're going to have an exothermic reaction. And what I mean by negative is think about it on a number line continuum. Okay? If here's 0 on my number line, here's 10, here's 2, we're moving in the negative direction on the number line there. Okay? Our delta H, we go from 10 kilojoules down to 2 kilojoules. We have decreased. We have a negative value there for our delta H. Does that make sense to everyone? Okay? And then obviously the opposite occurs with an endothermic reaction. We start off down here at 2 and we end up around 10. So we're increasing along a number line or along a scale. So our delta H becomes positive for a endothermic reaction. Okay? Now, where does that energy go? If we take a look at a reaction that we did 2 weeks ago, the balloons, we had 2 molecules of hydrogen gas reacting with 1 molecule of oxygen gas to produce 2 molecules of H2O. Okay? Again, numbers, I'm kind of making them up. Let's say with these 3 molecules over here, we had a total of 10 kilojoules of energy stored within those chemical bonds. Okay? I'm making up the number. The number itself is irrelevant. Okay? Over here, we now have just 2 kilojoules of energy stored within those bonds of the water molecules. Okay? Where does the other 8 kilojoules go? Okay? It goes into your surroundings, into your air. It's the heat you feel off of that chemical reaction. Okay? If you had been standing close enough to that balloon when it went off, you would have felt the heat coming off of that, the energy transfer, okay? The shock wave that was created by that rapid expansion of the gases. So what we do is we write the plus sign and we account for those 8 kilojoules on this side as a product. As we looked at on the previous screen, that is our exothermic reaction by definition. Questions? It also shows that we're conserving what throughout the overall system? Energy. Energy is conserved. You cannot destroy energy, nor can you create energy out of nothing. The energy has to come from somewhere. Yes? All right. Now, a couple of new terms that we have to throw at you. We go back up to these graphs. You see we've got a term called EA, and we have a term called AC at the top of our graph there. EA is the activation energy. Okay? All chemical reactions need a certain amount of energy to get started. With our balloon demo that we did 2 weeks ago, where did that activation energy come from for that reaction? Yeah, the flame or the candle that was in the can, right? Okay, that balloon was fine. We carried it outside. Somebody stood with it outside for a while. Okay, but until we applied that flame, the reaction didn't occur. So that flame, that energy from that flame was our activation energy. This amount of energy required to get up to this activated complex. Now, the activated complex, the best way to describe an activated complex is that it is kind of an intermediate. Okay? And when we come down here, okay, take a look at what we learned last semester. Think about the chemical bonds that we've got here. We've got two hydrogens bonded together with covalent bond, correct? We have one oxygen, which has a double covalent bond there. And then on the product side, we have two water molecules, each containing two single covalent bonds, yes? Now, the activated complex is this intermediate, this hybrid that exists for this millisecond as we transfer and change bonds. Okay? So it would look something like this. And again, I'm kind of sketching this out. We have our old bond that is getting broken between the oxygens. Okay? And a new bond getting formed between the oxygen and the hydrogen. And then again, there's this old bond that is dissipating between the two hydrogens. So that's our activated complex, kind of this intermediate where electrons are moved around. These are all shared covalent bonds, right? Sharing electrons here. So what we have is electrons being moved from the oxygen over to create a new bond with that hydrogen. This is our activated complex here, kind of our intermediate step, if you will. That intermediate step for the balloons didn't last very long, did it? Milliseconds. We light that balloon, we get enough energy, activation energy to get us up to the activated complex, and then bam! Balloon explodes, we all laugh, smile, think it's fun when the car alarm goes off, but really this activated complex lasts 4 milliseconds. It's not very long. Questions? Last thing we need to discuss on our graph here is the orange line. The orange line is what happens to a catalyst. We defined a catalyst a unit or two ago. What is the definition of a catalyst? It speeds up the rate of the reaction. Okay, so if you remember, we talked about the Haber process, where we have N2 and 3H2, which are in an equilibrium state with 2 ammonia molecules. Let's say, hypothetically speaking, the rate of this forward reaction here is 10 units per second. Again, I'm making up the number. The number itself is kind of irrelevant. That means that the reverse reaction is also 10 units per second because we've achieved equilibrium. Now, we throw the catalyst in here, and what changes? Yeah, both of the numbers change. They just go up. Now they're 15 and 15. Again, the numbers themselves are not important. It's the concept that whatever the rate is, the rate increases. Now, how does that translate into energy? We go all the way back up to this diagram here, okay? Now all of a sudden we see when we add this catalyst, okay, the amount of activation energy required to get to that activated complex, get over that hump in the graph, has decreased. Okay? Let's say hypothetically the activation energy required was 5 kilojoules originally. Well, now we add in that catalyst and it's less than 5 kilojoules, whatever the value is. It doesn't really matter. Again, I'm making up the numbers. The numbers are unimportant. It's the concept that when you add a catalyst into a system, it decreases the amount of activation energy required. Questions? All right, moving on. Let's go ahead and talk about the laws of thermodynamics. I'll give you a moment to copy that stuff down, and then we'll go over it. So, we defined enthalpy, which is H, the heat of reaction. Now we have entropy, which is a capital S. Entropy is the randomness or disorder of a chemical reaction. Any chemical reaction increases the entropy or the randomness of the universe. We are breaking chemical bonds, reforming new chemical bonds, and sometimes releasing energy out into our surroundings, yes? That increases the disorder of the universe. The universe is less organized after we blew up that balloon, okay? That leads us directly into the second law of thermodynamics. In any spontaneous process, there's always an increase in the entropy of the universe. Okay, spontaneous process, okay, combustion. When something combusts, again, reform new bonds and release a certain amount of energy. The first law of thermodynamics we've kind of already talked about, the law of conservation of energy. Energy cannot be created nor can it be destroyed. So the net energy at the start of the chemical reaction has to equal the net energy at the end of the chemical reaction. Even if the reaction releases energy, if we could capture that energy and measure it, we should have a net equal amount on both sides. Yes? All right, good. The law of the universe. We want minimum H for a chemical reaction and maximum S. Okay, as little heat of reaction as possible and as much randomness or disorder. Questions? All right, now that's kind of our general background information. We kind of dig down a little bit further now and start talking about calorimetry. This is what our lab is going to be on the next 2 class periods. So we're going to study this a lot in class. Give you a moment to copy this down. Calorimetry. When we study calorimetry, we're measuring the amount of energy, the flow of energy as heat. Energy can flow in 2 ways, from the system to the surroundings, exothermic, and from the surroundings to the system, endothermic. Every object has heat capacity, the ability to absorb heat that can be measured in a relative temperature change. So heat capacity, abbreviated capital C here, will always be measured in joules per degree Celsius. Now, if we want to be specific about the object itself, we have to add in a mass of the object. So that's where the specific heat capacity comes, which is a lowercase s. Now we take the amount of joules that are absorbed per gram per degree Celsius. Another way to think of it is, if I have 1 gram of copper, I heat that up 1 degree Celsius and measure the amount of heat it absorbed, I will now know the specific heat of copper. That will be a different number than, say, the specific heat of silver, or the specific heat of gold, or the specific heat of tin, so on and so forth, yes? Okay? Each metal on the periodic table is going to have a different specific heat that we could measure in lab, yes? Questions? So, a summary of what the statement that I just made there. Specific heat capacity is the energy required to increase the temperature of 1 gram of substance 1 degree Celsius. Now, obviously, we could do a molecular mass conversion and convert that grams into moles, and that would give us also a molar heat of capacity, which is joules divided by degrees Celsius per mole instead of per gram. And that's useful for comparing substances to one another, to have a molar heat of capacity. This all leads us towards our first equation for thermochemistry, which is Q equals ms delta T, where Q is the heat measured in joules, M is the mass measured in grams, S is the specific heat for the particular substance. Every substance is going to have a different value there. Silver, gold, water, etc. And then finally, delta T is our change in temperature, which will always be measured in degrees Celsius. Now, to be a little bit more specific, delta T is going to be the final temperature minus the initial temperature there. TF minus TI. We'll always subtract them in that order, regardless of whether the temperature increases or the temperature decreases. Because that makes sense to us, right? If the temperature were to decrease, then we would get a negative value, which means we've got negative heat for our system, correct? Because it is gaining heat rather than giving off heat. Questions? Two sample problems that I'd like to do as a class. Sample problem number 1, pretty straightforward. We got to do a conversion, and then we plug into our equation. I'll give you a moment to copy that down. So the equation that we're going to be using here is Q equals ms delta T, where delta T is TF minus TI. So I'll rewrite that. TF minus TI. Now, before we plug values into our equation, what do we need to convert? Yeah, we got specific heat has a unit of degrees Celsius here, and we have kelvins over here. All of your specific heats are always going to be Celsius. So I think the best thing to do is just convert kelvins into Celsiuses. So we subtract 273 here, subtract 273 here. We get 25 degrees Celsius and 0 degrees Celsius. At this point now, we're ready to go ahead and plug and chug. We're going to have our mass of 150 grams, our specific heat of 0.24 joules per degree Celsius grams, and then 25 minus 0 degrees Celsius. And that will equal our Q. Unit-wise, grams and grams cancel out, degrees Celsius and degrees Celsius cancel out. So Q is going to have a unit of joules. Yeah, this is the part where you pull out your calculator and start plugging away. It's always the language of the word problem. From 273 to 298. So our initial temperature is 273. Our final temperature is 298. You do have to pay a little bit of attention to the language to be able to determine which one is going to be TF, which one will be TI here. Mathematically, what do we get? 900 joules. We only want 2 sig figs, so it would be 9.0 times 10 to the second there. Questions? All right, problem number 2, slightly more difficult. First thing we want to do, without even thinking about it, is change what to what? Kelvin to Celsius, exactly. So we subtract 273 here, and we get 7 degrees Celsius. We subtract 273 here and get 57 degrees Celsius. Now, before we start trying to plug into equation and solve for this one, we want to think a little bit about what's going on. I have one sample of water that's at 7 degrees Celsius. I have another sample of water that's at 57 degrees Celsius. I'm going to take the 7 degrees sample and pour it into the 57 degree sample. That is going to give me water that has what temperature? That's what we want to solve for, right? We want to know what's the final temperature of the water. We know it's going to be between what two values? 7 and 57, right? Okay, so we know we're going to be somewhere between that range. How do we figure out what it is? Well, an important fact that's in here that doesn't have anything to do with the numbers is that we're assuming there's no heat loss to the surroundings. So, we know the 57-degree sample is going to do what? It's going to decrease in its heat. And the 7-degree sample is going to increase in its heat. Since we're not losing any heat to the surroundings, we can assume that the heat lost by the 57-degree sample is going to be gained by the 7-degree sample, yes? All right, so we're going to have the Q for the 7-degree sample and the Q for the 57-degree sample, yes? We said the 57-degree sample, its heat is going to increase the 7-degree sample, and the 57-degree sample is going to decrease. And since there's no heat loss, are those two values going to be the same? Yeah, so we can set those equal to one another. Right? Okay, so now what I'm going to do is instead of Q, I'm going to go ahead and substitute the rest of the equation in there. Q equals ms delta T, yes? So now we're going to have plus ms delta T for the 7-degree sample equals negative ms delta T for the 57-degree sample. Everybody still with me? Does that make sense what I just did there? Now we can go ahead and start plugging in some values, yes? Okay. The 7-degree sample we said was 50 grams times the specific heat of water, 4.184 degrees Celsius, TF minus the 7-degree sample, 7-degree temperature, excuse me. Now I wrote equals, and I wrote the negative, because remember, this 57.1 needs to be negative. It's got to decrease. Oh, wait a minute, did I get my numbers backwards? I did, didn't I? Yep. This one's 30, not 50. Excuse me. Right? Your 50-degree sample is the higher temperature one times its specific heat. And then, of course, I ran out of room. So we have TF minus 57 degrees Celsius. Oops. Questions? All right, seniors, by the look on some of your faces, I need to go through the algebra step by step here, don't I? Yes. Okay. So first thing we got to do is 30 times 4.184. What do we get? $125.52, which is going to get multiplied by TF minus 7 degrees, and 50 times 4.184. $209.2, which is TF minus 57 degrees Celsius. Okay? Remember, don't forget the negative. Don't lose that negative in this problem. Now we'll distribute. So we get 125.52 TF minus, what's 125.52 times 7? 878.64. And that's going to equal a negative 209.2 TF minus, negative times a negative is positive, excuse me. 209.2 times 57. All right. Now we need to move the values. We're going to move this one to this side, and we're going to move this value to this side so that everything's positive, right? Okay, so we get what for TF? It is 334.72, yes? Is that right? Somebody checking my math? Okay, good. And then on the other side, we get 12,000 something, something, something. What is it? All right, last step, divide both sides by the 334.72. And we get a final answer of 38.25. Now, Mr. Sutton got a little sloppy. He kind of dropped his units as he started to do the algebra. Temperature has what units, though? Degrees Celsius. Yeah, don't forget to add your units at the end of the problem. Any questions? All right, excellent. We're done.